So for the past few years, I've been working on this hypothesis for quantum gravity, or this quantum gravity theory, if you like. And the cosmological implications of this idea may be somewhat profound, in my opinion, since I only came across this idea rather recently, and I was toying around with a rough sketch of an idea that I've had, and other people have had, by the way, for rather a long time concerning dark energy. And my quantum gravity idea, the very basic assumption of it, is that gravitational fields are formed of electron densities. So in exactly the same way that a hydrogen atom's nucleus has an electron density surrounding it, objects made of atoms have a sort of residual electron volume probability density associated with them, emanating from all the atomic nuclei forming those objects. And these electron densities, the density of it, the concentration of electrons within an electron density, falls off according to Newton's inverse square law for gravity, i.e. it falls off according to 1/r squared. So yeah, as you retreat from the surface of an object, or its apparent surface, if you like, you encounter fewer and fewer electrons comprising the gravitational field of these bodies. Now, my idea to do with dark energy was that dark energy is, in essence, just radiation pressure caused by all the photons released from all the galaxy clusters in the universe since the beginning of the universe, just building up between galaxies, and the radiation pressure generated by those buildups causes these galaxies to expand. But what we know about the expansion of the universe is that it's not merely expanding, but it's accelerating, or that expansion is accelerating. So we need to come up for a reason why this is the case, why galaxy clusters seem to accelerate in their motion away from one another. So I came up with this notion that in addition to all the photons being emitted from galaxy clusters that just end up between galaxy clusters, relatively unimpeded by the electron densities within any given galaxy cluster, summed up from all the planets, stars, and so on, there is an additional effect which somewhat explains the Casimir force. It has applicability to Hawking radiation. And this is the effect that since these electron densities are formed of tunneling electrons, and each electron stays in position about once every Planck, or changes position once every Planck second, and moves to a different location, whereupon it emits a photon and or absorbs another particle. So the idea, I guess, is roughly that electrons tunnel from one point in the universe to another, of the galaxy cluster to another, tunnels to the edge of a galaxy cluster, emits a photon into these recesses of intergalactic space where these photons are building up. And because the number of electrons in the gravitational fields of galaxy clusters is constant, unchanging, and remains determined by the mass present within any given galaxy cluster, and because also the number of photons within these recesses of intergalactic space is increasing, the reuptake of photons via these secondary density electrons is somewhat limited. So they can only take back the same number of photons each time. However, photons are constantly being added to it. So there's more and more photons in the spaces between galaxies. The electrons take back some of them by quantumly tunneling, absorbing a photon, coming back with it, depositing it back into the galaxy, or the galaxy cluster. And hence we get acceleration in expansion of the universe. However, the implication of this idea of photon reuptake by background or secondary density electrons implied to me something rather peculiar. And this peculiar thing that it implied is that the cosmic microwave background radiation that serves as evidence for Stephen Hawking's Big Bang cosmology might actually not come from the beginning of time. What that actually might be is microwave radiation leaking back into this galaxy. So, what happens when photons leave very strong gravitational fields is that they become redshifted. They lose energy, in essence. Since in my model with background electrons, um, electrons remains at high energy when it has a high probability of being absorbed again by a background electron. So, like these zigzag lines that we do when we're talking about photons, like gamma rays, say, um, yeah, those are they're literally being absorbed and emitted again at an angle of 31 degrees to the angle of incidence by a background particle. So it means that at any point between two electrons, they're probably moving faster than light. They just move in a straight line at light speed at c. Maybe they're moving at c squared, I think. And yeah, so because there are progressively fewer and fewer electrons when you're getting into these recesses of intergalactic space, all these photons, they expand outwards and turn into something more like a microwave or more like a radio wave. And the electrons from the galaxy clusters tunnel, they pull some back in, and we get a burst of an emission of microwaves back into the galaxy, and so on. But that doesn't really alter the fact that very distant galaxy clusters and galaxies are moving away from us. And we know this because they're redshifted, right? So, or the light from them is redshifted. I mean, you can see Andromeda is moving towards us. The light is blue shifted. Okay, so we know that like some galaxies are moving towards us. Most galaxies are moving away from us. I think the implication of this is that we might be living in some sort of quasi-steady-state model, that the universe undergoes periods of expansion, periods of contraction, and it's much more like a breathing in and breathing out, swelling, collapse, maybe at points to singularities, even. So maybe Stephen Hawking is not entirely wrong, actually, to suggest that singularities emerge. But I'm tempted to think that maybe there's just periods of higher and lower concentration, and that this cosmological principle of the universe being homogeneous and isotropic over very long periods of time actually doesn't hold so well. So yeah, I mean that's my idea, I think. Or well, many other people have contributed to the idea, I think, and it's somewhat obscure in physics currently, I think, or cosmology currently. But I think it's certainly along the right lines, this suggestion. And it would need to be also this effect of electron emission by electron densities themselves doing this, for the reason being that if it were just light emitted from galaxies building up between galaxy clusters, there would be no acceleration. The expansion of the universe would just follow a uniform straight line. There would be no curve in the acceleration, because you'd have on the one hand electrons emitting just a touch more radiation to the recesses of intergalactic space, as I've mentioned, and likewise they would be absorbing photons from those regions of intergalactic space and bringing them back into the galaxy, unless there's this effect of electron drift, so-called, I've sort of been playing with, where it tunnels to just another point in the universe, and then another electron pops up to take that electron's place, and the other electron absorbs a photon, tunnels somewhere else, and so on. I'll be playing around with like very kind of stochastic Poisson distribution-esque processes, I think. Nonetheless, I think the effect would still be the same, because for all intents and purposes, in sort of quantum classical domains, the electron density of a galaxy cluster is constant. However, new photons are constantly being added to it via direct emission from galaxies and via this tunneling process. So you can think of this tunneling process, because this would also give rise to Hawking radiation. So an electron in the gravitational field of a black hole would tunnel to within the event horizon of a black hole, absorb a photon there, jump out, emit it. And this is probably going on all the time. And the overwhelming majority of photons emitted into the regions of a black hole's gravitational field closer to the event horizon, almost all of them would fall back in straight away. Some would manage to escape and become redshifted when they're a bit further away from the event horizon, quite a bit further away. But yeah, it's very interesting. I think it's a very interesting idea, certainly. And using these sort of electron density notions to think about cosmological ideas and astrophysical ideas, black hole physics, etc. Yeah, very, very cool, I think. And I think it's likely, I think it's very likely that this physics is correct. So yeah, it's needed, I think, on a level. And if we just had electron densities that didn't do this, that didn't absorb and emit photons, as from what we know about electrons, I suspect it's very likely they are constantly absorbing and emitting photons or other particles, and other particles, because that would also be necessary in my model. Without this, you would just have the reflective capacities of these galaxy clusters and the lights emitted from them. And the light would just be bouncing back between galaxy clusters and be expanding at a uniform and not accelerating rate, I think. I'm pretty certain. So yeah, thank you for watching. Bye.